Okay, so we move on to our next speaker, Michał Matuszewski from Institute of Physics at the Polish Academy of Sciences. Michał, the stage is yours. Please take away.
Thank you very much. Thank you for the introduction, and I will try to share my screen. Okay, yeah. So thank you for the invitation to give this talk. In my talk, I will try to make it as quick as I can. In this talk, I would like to tell about optical computing with exciton-polaritons. This is actually, for me, this is a new field. I'm just in this field for a few years, and that's why I also would like to see some comments on this work and questions if there are arise some. And during this time, we were working on the system of excitons-polaritons, which haven't been used for optical computing yet, and I will try to show their advantages. So this work has been done in collaboration with several groups. So I would like to underscore the work of my PhD student Andrzej Opala, and also collaboration with experimentalists from the University of Warsaw and CNR Nanotech in Lecce. So first, I would like to give some motivation. So as we know, in these days, there is a lot of increase in energy consumption, electrical energy consumption in the world, and much of this energy consumption actually comes from electronic devices. So if we look at the analysis for the share of energy consumption in communication technology in general, depending on the scenario, we might have 20, even in the worst case, to 50% of energy consumption due to the communication technology by 2030. And this is related to the fact that for some time we see departure from the Dennard scaling. Dennard scaling is a, let's say, law that states that as the density of transistors per millimeter squared increases, the power consumption per transistor decreases, so the power per surface of a silicon is constant. And thanks to that, as the computer power of silicon grew with each new generation, computers became more and more energy efficient, but we could use them with the same amount of energy. But unfortunately, at some point, this law became too saturate. So the question is if we can do something with photons. So actually, for a long time already, it has been proposed that photons could be used for efficient information processing, because communication with photons is associated with much lower losses. That is why we are using photons for communication, such as in waveguides. And actually, as the data rates become higher and higher, this difference between electrons and photons becomes more pronounced. So at current data rates, it is useful not only to use photons for long distance communication, but also for communication between different workstations, or even between different chips. And this is already applied commercially. So the problem with photons is that they are very weakly interacting and only in nonlinear media, whereas electrons are characterized by substantial interactions. So if we want to construct a system which performs useful information processing, such as transistor or neuron, then we need this nonlinearity for it to function. So I would like to give first a brief overview of the history of optical neural networks, because this concept is actually quite old. Already in the 70s, there were some experiments which demonstrated in which people have tried to use optics for implementation of tasks such as vector matrix multiplication. And they were successful. Actually, it is thanks to the properties of Maxwell equations, it is easy to propose and construct a system which performs vector matrix multiplication. So we just need a set of sources, for example, array of LEDs, then a memory mask, which can be implemented by some material which has a transparency which we can program, and then put a row of detectors and a certain system of lenses on its way. And this system can perform multiplication. And of course, vector matrix multiplication is one of the most important operations that are needed for neural networks. Later on, it was proposed that one can use, for example, holograms to even increase the capacity of this memory mask, let's say, to include it in three-dimensional space. So these experiments were quite promising, and they actually displayed quite a wide range of functionality, but they were never applied in practice. They were not able to compete with electronics. And there were several reasons for that. So one of the reasons was that the rapid development of electronics according to Moore's law. Another was that digital electronics were able to perform universal operations, whereas photonic devices could only perform application-specific operations. Optical systems were impractical because they are quite bulky in comparison to on-chip integrated electronics. And finally, apart from communication, where photonics found applications, a practical advantage of photonics in speed or energy efficiency has never been demonstrated, and this is in part due to the weakness of nonlinearity. So nowadays, the situation is quite different because Moore's law is no longer valid. There is a growing need for application-specific devices, such as GPUs and TPUs, that basically perform only specific operations, such as vector matrix multiplication. Photonics can be now integrated on a chip, as I will demonstrate in a few slides. And the advantage of photonics, I hope that it will be demonstrated in the near future. So I would like to show now a few examples of recent experiments that in which approach this problem of optical neural networks. So the first of them is this concept of broadcast and wait network, which is implementation of neural networks in silicon integrated photonics, which is based on micro-ring resonators, wavelength multiplexing, and balanced photodiodes. So basically we have signals that are encoded in frequency of photons that corresponds to different synapses. Each synapse has its own ring resonator, which performs the weighting. And then there is a balanced photodiode, which can generate electrical signal, which can be either positive or negative. So we can have positive and negative weights. Then there is an electronic system which integrates the signal and generates output for new neurons. So this is an optoelectronic device which performs operation of neurons, of a single neuron at this figure. Another very interesting work was done in a system of Mach-Zehnder interferometers that actually can realize an arbitrary linear operation using unitary and diagonal transformations of coherent light. So it is known that any linear operation can be decomposed into one actually 2 unitary operations which change the basis, and a diagonal operation which only attenuates signals on the diagonal. And this operation can be, all these operations actually can be realized in a system of Mach-Zehnder interferometers. And another example is diffractive optical networks, which work on quite different concepts. So this is not an integrated system, but a system where the light propagates in free space. And on its way, there are several plates which are patterned in such a way that the optical signals that propagate between the plates realize operation of a neural network. So if we have input that corresponds to a sample that we want to process, the detector at the output will detect the signal corresponding to the particular class. So this was demonstrated in microwaves, but also recently in the optical domain. And finally, of course, there is optical reservoir computing, but I will not talk about this because it was already covered very well by Yoni. So if you would like to read more, I would recommend these 2 very recent reviews, which cover this topic very, very nicely. Okay, so now I would like to go to Polariton neural networks. So why are we interested in Polariton neural networks, and why we think that they are an interesting concept for optical neural networks? Well, as I mentioned before, the advantage of photons is that they are low loss. They can exhibit low loss at high data rates. However, excuse me. However, the disadvantage is that photons are very weakly interacting. So the question is, can we maybe have substantial interactions, such as for electrons, and low communication losses at the same time? And the idea is the following. We can use exciton-polaritons, which are hybrid particles, which are both matter and light particles. Exciton-polaritons occur in microcavities where light enclosed in a cavity is strongly coupled. There is strong quantum coupling to excitons in a semiconductor quantum well. So actually the correct quantum description of exciton-polaritons is in terms of new eigenstates, quasi-particles, that have the properties of both light and matter. And thanks to this hybridization of light and matter, these particles have both excellent transport properties and extremely low effective mass, thanks to this photonic component, and very strong interparticle interactions, thanks to the exciton component. Actually, it is a world record of ultra-fast optical nonlinearity. So if we want to describe exciton-polaritons in a proper quantum way, the simplest model looks like this. So we have annihilation operators for excitons, which are approximate bosons, photons, also bosons, and strong coupling between them. So we have exciton excitations, photon excitations, and coupling, which looks like this, that there can be creation of exciton and annihilation of a photon, and reverse process. This process are possible. So it is easy to show that this simple Hamiltonian can be diagonalized, and that we can find new quasi-particles that are eigenstates of this Hamiltonian. So in this figure, I show the dispersion relation for exciton-polaritons. So this red curve and green curve are dispersions of uncoupled photons excitons. So dispersions in the absence of this coupling term. The photon dispersion is parabolic because a photon enclosed in a microcavity has a in function of momentum parallel to the surface of the microcavity plane is parabolic. So the photon actually has an effective mass which depends on the geometry of the cavity. The exciton also has a parabolic dispersion relation because it is a massive particle. However, its mass is orders of magnitude larger. So in this figure, it is practically a vertical line. And now if we turn on this cupping term, we get two branches, upper and lower polaritons. And in this region of anti-crossing of these two dispersions, we have both upper and lower polaritons are quasi-particles which are mixed particles of light and matter. So there are many works in which exciton-polaritons have been applied and investigated for example, for simulation of certain physical systems such as XY model, Hawking radiation, ferromagnetic and antiferromagnetic phases, for lasers, topological lasers and detectors, and also for devices such as logic gates, switches, and so on. And we propose that they can also be used for neural networks. So the first concept that we had is based on reservoir computing. So I think I don't have to go through it because it's already has been quite well described. So our idea of building the reservoir was the following. We consider a system of microcavity pillars. So basically this is a microcavity sample which is patterned in such a way that there are pillars. Each of these nodes is actually a pillar, which are coupled with each other. So each of these pillars actually contains a quantum well and two Bragg mirrors, which are not visible on this micrograph. And these pillars host polaritons. And these polaritons can tunnel between different pillars. And a model which describes very well this system is based on discrete complex Ginzburg-Landau equation, which looks like this. We have a resonant injection, which corresponds to a resonant laser, which basically shines input pulses from the top or from the bottom. There is coupling between the pillars due to tunneling between them. There is pumping, non-resonant pumping, and linear losses, which are always occurring, non-linear losses and interactions between polaritons. And these interactions actually come from these exciton components. And our theoretical idea was the following. We use this network for classification of hundreds and digits. To do this, we convert the image of the digits to time-dependent series. We multiply the signals by random matrix to distribute the signal on the whole lattice reservoir, which this operation improves efficiency actually. And then we monitor emission from these pillars and use them as outputs from the reservoir. So this lattice is basically a reservoir, and then we perform standard classification by linear classification as described in the previous talk. So this part is actually performed in software. So this linear classification is on a computer. So we found that this Polariton reservoir works the best at the threshold of condensation. So I didn't mention it, but in a system of exciton-polaritons, there is a phenomenon of Bose-Einstein condensation. I don't want to go into details on that, but basically this is a phase transition. So this is kind of like a threshold for some kind of loss of stability of one solution and appearance of another stable solution. So we found that the Polariton reservoir works best exactly at this threshold or phase transition, which is basically agrees with the nonlinear threshold concept. And what is interesting that potentially we found that this system can be quite efficient. So this is of course only numerical estimate, but we found that because of the natural timescales which are present in microcavity Polaritons, which are on the picosecond timescale, we can, for example, for the task of spoken digit recognition, we can estimate that this recognition can be performed much faster than in previous systems. So now I would like to go to experiments.
Michał, can I just ask you one question from your previous, not the slide before this one? So you said it works best at the threshold of condensation. What's the role of coherence here?
Okay, so actually, it is a good question. So because we are working in the model when we have resonant pumping, so we are kind of injecting the coherence from outside. This would be different if we use non-resonant pumping, and then the coherence would appear during condensation. Then it would, but in this system, actually, I don't think that coherence is actually, there is probably not much difference in coherence between left and right side.
Thanks.
Okay, so now I would like to, actually, if there are any questions, please, please ask. Okay, so I would like to now describe some experiments that we have done with our colleagues. So the first experiment was more or less based on the idea that I described previously, but here instead of time-dependent signals, we used spatial encoding of information. So basically this digit was multiplied by a random matrix and encoded in the light transmitted by a spatial light modulator. Then this optical signal was incident on a sample, Polariton sample, which was characterized by a highly nonlinear response. Finally, this transmission of light was recorded by a CCD camera, and it was the final output layer was implemented in software again. So we found that our system is able to process MNIST dataset with 93% accuracy, which is, well, it is not very high as compared to software, of course, that can reach 99.7 or such accuracy. However, if we compare to other hardware implementation, it is quite good. And particularly important is that we obtained a result that is higher, significantly higher than linear classification threshold. So it means that our nonlinear reservoir actually brings something positive to the system. So the system would work worse if there was no reservoir here.
Michał?
Yes?
Question here. What is efficiency here, the metric you're using on the vertical axis?
Sorry, I should mention that. So this is the percentage of correctly predicted digits. So this.
Okay, it's just error rate. Yeah.
Yes, so this is 1 minus error rate.
Mm-hmm.
Excuse me, can I ask one more question? So in your previous slide, when you were talking about encoding your MNIST data into your system, so I assume now those vectors, when you multiply by a matrix 2, is just like a continuous variable. How you are encoding those into your system?
So exactly. So we have MNIST input. We multiply this input by a random matrix. So this matrix is random, but it is fixed in for all the digits. So it is not changing this is very important. And then it is this information is used for encoding light, like how much light is incident on the sample at each point. So the spatial light modulator allows you to kind of create any kind of pattern of light on the surface of the sample.
Thank you.
Okay. So we obtained this error rate, and now also I would like to mention that potentially this, maybe not in this work, but potentially this system can be characterized by a very high speed, because we have polaritons that work with picosecond timescales. So it means that we can even think of terahertz processing speed for this system. Okay, so another experiment that we implemented was based on binarized neural networks. So what are binarized neural networks? These are networks in which activations or weights of connections are two-level, and the neurons perform simple binary operation. And these networks are characterized by greatly improved speed and energy efficiency at the cost of minimal reduction of inference accuracy. So the building block of a binarized network is usually a neuron that is performing a simple binary operation such as exclusive OR. Why exclusive OR? Because this is an operation which is highly nonlinear. It cannot be performed efficiently by a linear system. It can be seen on such a graph. If we have two inputs, so this is like two legs of the gate, and we have either 0 or 1 at each of the inputs, and we want to distinguish the cases 0, 0 and 1, 1 from 0, 1 and 1, 0. It is easy to see that we cannot draw any straight line that will separate these two cases. So we cannot use just linear classification for this problem. We can, but we will never reach 100%. However, if we have nonlinear system, so we add another dimension on this graph, which corresponds to a nonlinear features, which is some kind of a combination of these two inputs, and it is sufficiently nonlinear, then in certain cases we can draw a plane which will linearly separate these two cases. So if we can perform this XOR operation, it means that we have highly nonlinear system. And actually, it is also relatively easy to implement experimentally such a gate. So this was also one of the motivations for this experiment. So we designed and constructed such a network where neurons were realized as exclusive OR gates. So it was realized in such a way that there were two optical pulses, and each of them encoded 0 or 1 in the intensity. And we monitored the output intensity and used this output as an output of a layer of such simple binarized neurons. And there was a linear classification performed in software in this first proof of principle experiment. However, this was only a linear operation, and all nonlinear transformations were realized entirely by this nonlinear optical gates. So what is important that the output from this from Polariton sample is highly nonlinear and actually reminds sort of a ReLU function used for neural network applications. So we used time multiplexing to realize such a hybrid optical electron neural network, and we found that the classification was actually, again, quite much higher than for linear regression, linear classification alone. And we achieved 96% accuracy, which is comparable to state-of-the-art hardware realizations. And further, we were considered whether we can go further with this concept and realized all-optical system. And we realized an all-optical gate by using additional light paths described by W1 and W2, which were encoding the weights of inputs, linear inputs here, whereas the transmission from, again, through the sample was used as a nonlinear feature, so the z-axis. And again, here we obtained very good operation of this gate and quite good efficiency of 60 picojoule per synaptic operation, which is very much comparable with the best electronic realizations. Okay, so finally, I would like to give some outlook on Polariton neural networks. So why we think that they are promising? Well, it is instructive to consider a nonlinear phase acquired by an optical pulse transmitted through a Polariton microcavity. So let's say that we have a pulse, it is transmitted through, and then output pulse is similar, but it acquires some optical phase. And if we can achieve a pi shift, it means that we can perform a useful operation, because then we can use this pi phase shift to, for example, using Mach-Zehnder interferometer to completely block or let transmission of the pulse. And the approximate condition for this operation for this transmission to achieve pi phase shift is given by this formula. So the nonlinear energy has to be higher than Polariton lifetime or photon lifetime in the cavity, where n is the average exciton density and g is the exciton interaction constant, and this is actually inverse lifetime of photon in a cavity. And we can calculate that the simple calculation gives about 3 attojoules energy cost, which is about 4 orders of magnitude lower than for any other nonlinear media. And then we proposed an all-optical neural network for very efficient inference. And basically it looks like this and performs a single hidden layer network for classification. So we have input, optical input, in the form of pulses which arrive in parallel on the sample. Each of the nodes have like 2 legs, because we again considered exclusive OR gates in this case. Then the output, which is nonlinear, is split into m copies, where m is the number of classes that we want to consider in this task. And then we have a weight bank, which for each of the classes applies particular weights. And there are no electronic elements in this network, except for light modulators at the input to create this optical sequence of pulses, and the detectors at the output. And these optical weights can be implemented in a standard 4F system in a liquid crystal array or phase change material. And these weights don't have to be tuned during inference, which is very important, because tuning means manipulation of these weights, which usually requires quite a lot of energy. And we estimated the energy efficiency of the system by taking into account energy cost of a light source, modulators, detectors, and optical losses. And we considered 2 cases of a kind of idealized system with parameters corresponding to state-of-the-art elements. And B is the proof of principle system, where a relatively small number of nodes and only accessible optical elements. But we see that in both of these cases, we can expect improvements over electronics in energy efficiency and processing speed. Okay, so finally, I would like to mention some challenges and future works that we are planning to do. So we have to demonstrate experimentally a large-scale network, Yes, because so far we just implemented several neurons. We have to implement multi-layer networks. We need signal generation and fan-out, which is not easy. We have, for efficient operation, we need room temperature operation. But there is actually a number of materials in which exciton-polaritons have been observed at room temperature. So this should be doable. And we need also some efficient interface between electronics and optics at the input and output of the network. However, this is actually something that is common for all optical implementations of optical computing. Okay, so in conclusion, we demonstrated theoretically and experimentally that exciton-polariton systems are powerful platform for machine learning. And our estimates indicate that we can think of orders of magnitude improvements over electronics in terms of speed and energy efficiency. So thank you very much for your attention, and I will be glad to hear some questions.
Okay, so Michał, thank you very much for this interesting talk. I think we have several questions, some of which have been resolving themselves through self-organization among attendees here. And we have time, so it's 10:45 now, and to remain on schedule at 11 o'clock. We are 15 minutes into our break, so we have another 15 minutes. And so my suggestion is that we, whoever is interested in discussing and asking questions, let's use this time for that. And others who need to take a break, they shall do that until 11 o'clock. Yeah. Okay. So do you want to look at the chat box to see?
Yes, sure.
So there is one question. Yeah, so there's some question about references. You can probably put it on the chat box later on. There's one question from Graham Rollins that you may want to.
Okay, I think I have to. I don't see the chat box. I think.
Okay. Let me read it to you. So terahertz speeds sound really nice, but you are still doing software weight multiplication in a way to use SLMs or something else to do weight multiplication at those speeds. I think this came early on before you presented your later slides, where I think you're attempting to do that. But I think there's a general question of processing speeds and some details regarding experimental implementation that would be interesting to discuss. Yes, generally.
Okay, so should I answer them now or in the break, during the break?
Yeah, we are in the break, so maybe now we can you can take those questions.
Okay, so I think I have to stop sharing because only this way I can look at the chat box. Okay.
Or we can simply ask Graham. Do you want to just unmute yourself and ask your question?
Sure. Yeah, sorry.
Yeah,
I can't see myself here. Yeah, this did come before your kind of discussion of the all-optical approach. But with the kind of the single SLM, where you're doing the digitization, and I'm assuming that the post-processing was all done in software. And I was just curious, using that scheme, which is actually very simple, in the scheme of things, is it possible to somehow offload that weight multiplication, since that's something we already kind of know can be done potentially with like a matrix vector multiplier in the optical domain? Is there any way to kind of get that whole scheme working purely in the optical domain?
Yeah, so actually this is what we are attempting to do. So maybe I can share screen again. So this is the whole kind of point that we don't want to use SLM for we need some kind of weight banks for applying the weights, but we want to do it in such a way that these weights don't have to be tuned during the inference. So let's say we can have many optical inputs, and these optical inputs can be generated, for example, by using high-speed modulators, which can work in the picojoule energy scale. And we don't need any SLM here. So this SLM here doesn't have to be changed as long as we are doing the same task. So if, for example, if we have to process, I don't know, thousands of samples, different samples of input, then we don't have to change the SLM. And this is important because changing the SLM is a certain energy cost that we want to avoid. And in this sense, this is all optical. Of course, we need some kind of interface between electronics signal and optics. So we need some kind of tool to convert electronic signal into optical. But there are ways to do it efficiently.
Great, thanks. I appreciate that. I realized that you treated this after I'd asked the question. So, but just to clarify, thank you very much.
It's not necessarily the efficiency that really matters. You know, the bottleneck in almost all physical reservoir computers is how do you get the classical data from RAM pushed out into the system? There's an energy cost with retrieving that from the RAM, and then whatever modulator you use, it might be energy efficient, but it tends to be slow. So a lot of the reports that are out there on physical reservoir computers are only talking about the core reservoir. But it's really that bottleneck of getting the data in and out. In the end, you're going to have to interface with standard computer hardware. And so that is almost always the bottleneck.
Yes, sure. So actually, we are aware of that. So we assume from the outset that if we want to inject some information into the system, we need, let's say, picojoule per bit energy cost to do that, because this is the cost for retrieving data from the RAM, for example. However, the point is here that usually in neural networks, the number of input channels is much lower than the number of neurons. So we want to use this kind of difference in scales. And that's why by using all optical elements, we can kind of divide this cost of retrieving from RAM through many neurons, many synaptic weights, and so on. And this is kind of advantage of this all optical approach.
Mm-hmm.
We have some raised hands here. Can you please unmute yourself and ask your question in some order? Maybe Kevin.
Yeah.
First stands with us.
Do you hear me?
We do.
Yes.
Yeah. So my question was mostly about energy efficiency, because you say it's the order of picojoule per operation, but can detectors detect this amount, or you need to average over multiple pulses or something?
Okay, so the picojoule efficiency that I am talking about is kind of what I know about the literature, what is the efficiency of modulators or detectors. However, the energy per operation in the system is actually much better, because if we kind of divide this cost by all the neurons, if we can have many neurons in this system, they can actually work on much lower energy scale. So we can expect like tens or hundreds of attojoules even in the best case. And now, as detectors are concerned, well, if you consider that in many classification tasks, for example, you have, let's say, for the MNIST classification task, you have only 10 classes, so you only need 10 detectors at the end. If you have ImageNet, you have 10,000 classes, so you need kind of 10,000 detectors, but the number of neurons and number of operations that you perform in your network is orders of magnitude higher. So actually, we also consider this detector efficiency, but we found that it is not the main kind of bottleneck of efficiency of the system, at least in the tasks that we consider.
So wait, you're basically saying that your information is spread out in the reservoir and then is focused back onto the output, and so the energy efficiency is only in the output then.
Yes. So we need to have let's say picojoule energy in the optical pulse that is arriving on the detector, but it doesn't mean that we cannot perform operation inside the network at much lower energy scale.
So it's 10:54. I think this is about it. So thanks again, Michał.
Thank you very much.
It was a good discussion. I suggest we resume in 5 minutes. And I will see you all there.